Our home is a medium-sized planet, third in a solar system located in the corner of one of several million galaxies. How does this planet operate and support life? What processes created and sustain the sun and other stars? Indeed, how did the universe begin and evolve? Two of the most powerful tools in answering such questions are observations and supercomputers. NASA observations include telescopes pointed at the heavens, spacecraft studying other planets, and satellites recording the climate and even the life forms of Earth. Supercomputers, on the other hand, create mathematical models of the inner workings of nature in places that observations can and cannot reach. But often billions, even trillions of bytes of data result in a form that is not easy to understand. To make sense out of all of these numbers, researchers turn them into colorful scientific visualizations. From the inviting and familiar waters of our oceans to the eerie contours of a distant black hole, NASA and scientists it supports are gaining unprecedented insights through images of Earth and space. Of vast size and complexity, the world's oceans do not remain in their normal state. The biggest irregularity is El Niño, the periodic warming of the eastern Pacific Ocean. Depicted here, the 1982-83 El Niño was the largest of the century, contributing to floods and droughts that caused 1,100 deaths and $8 billion in damage. Light orange indicates warmer than normal sea surface temperatures, and dark purple, colder than normal temperatures. From the ocean, we move to the atmosphere, where midway up ozone, made up of 3 oxygen atoms, absorbs harmful ultraviolet radiation from the sun. Its depletion, therefore, has negative impacts on the health of animals and plants. Observations such as these in 1991 show that ozone concentrations are declining over the whole globe, partly due to human causes. The most pronounced decrease is above Antarctica, a phenomenon scientists have dubbed the ozone hole. Clouds play a critical role in regulating the Earth's temperature, with an overall effect of surface cooling. These animated sequences show a 1-month sample of composite images from cloud cover and temperature data collected by a suite of U.S., European, and Japanese weather satellites. More than 12 years of data have been gathered, with an average of 1 billion bytes each month. Satellites also probe the Earth's surface for features that are difficult or impossible to reach by other means. Mountain glaciers, for instance, have generally been receding over the last century, making them excellent indicators of climate change. One telling region is southeastern Alaska's Glacier Bay. Notice how the tidewater Muir Glacier significantly retreated from 1973 to 1986, a total of greater than 7.3 kilometers. A flyby sequence gives a bird's-eye view of the snow accumulation, the slope and aspect of the glaciers, and most importantly, the snowline elevation. The higher the elevation, the more melting that occurs. How such a changing planet supports living creatures can be seen in this visualization of the biosphere, the life zone of the Earth. It shows a combination of land sensing, vegetation index, and ocean sensing and color data. On land, dense vegetation is green, and sparse vegetation is light yellow. Ocean coloring is due to phytoplankton pigment concentration. As the first link in the marine food web, phytoplankton mark the habitats of other ocean dwellers. Areas along coasts have high biological activity, shown in red. Purple indicates low biological activity. 99% of the biosphere is found in the oceans, and with it a large diversity of species. This world within a world is also home to some of Earth's greatest extremes, from the tallest mountain to the deepest trench. Because much of it is unreachable, some scientists compare the ocean to other planets, which can only be studied with the most ingenious of methods. Our closest planetary neighbor is, of course, the Moon. The Clementine spacecraft mapped the entire lunar surface over several months in 1994. A 3D perspective view of the data provides a detailed portrait of the rocky landscape. Heights are exaggerated 7 times to allow closer study. A simulated flyover shows the dramatic topography of many ancient basins. Among other discoveries, mission scientists found that the South Pole Aitken Basin, likely carved by the long-ago impact of a 200-kilometer-wide meteoroid, is the largest and deepest in the solar system. At 2,500 kilometers, it is 1/3 the size of the United States. Space flights like those to the Moon affect the human body in many ways. One investigator is studying the different forces that act on the musculoskeletal system on Earth and in space. Supercomputers model multi-joint coordination and muscle function during complex motor tasks such as walking. In the summer of '94, many human eyes witnessed the collision of Comet Shoemaker-Levy 9 with Jupiter. Here are the results of a simulation of its initial breakup using a swarmed comet model. The scientists assumed that the tidal field of Jupiter broke the comet into approximately 1 million small fragments. The swarm of fragments becomes gravitationally unstable and accumulates into roughly 20 to 30 clumps, which is consistent with the 21 fragments observed before impact. From the light show of the comet, we travel to the deep interior of a boiling sun. The visualized simulation shows the temperature fluctuations in the upper 2/3 of the sun. Dark colors show cooler temperatures, light colors, hotter temperatures. The unstable and turbulent upper layer convects or transfers energy from the stable lower layer. Thermal plumes moving onto the lower layer generate gravity waves, which causes the gas to mix. This process, called convective penetration, is a fundamental component of the sun's structure. Streams of protons, electrons, and helium ions make up the constantly flowing solar wind. Faster particles travel from the poles, while slower particles move about the equator. The sun's rotation mixes these currents. Once past Jupiter, they form a vortex street in which magnetic field lines are trapped in particle whirlpools. A supercomputer model provides insight into these structures. The prominent purple tubes are areas of low particle density. Inside are the thin orange lines of vortex regions, spiraling and coiling as motion becomes tangled and particles collide. While seemingly fragile, a typical vortex is 1.6 billion kilometers across. 750 light-years away from our Sun is a 2-star system known as R Aquarii. In orbit around each other, the smaller, hotter star grabs mass being lost by the larger, cooler star. More astonishing is the existence of a 2-sided jet, a supersonic stream of matter that appears to emanate from a disk of material forming around the hot star. Scientists used a 16,000 processor parallel computer to restore flawed images taken over 2 years by the original uncorrected Hubble Space Telescope's faint object camera. One of few movies of actual jet data, It reveals for the first time the gas jet's motion along the northeast-southwest axis. At the end of their lifetimes, some stars exhaust their nuclear fuel and either collapse into black holes or explode as supernovae. Supercomputers are crucial for finding the causes and studying the dynamics of these phenomena. A black hole's gravitational pull is so strong that not even light can escape it. Here, a gravitational wave traveling at the speed of light crosses the surrounding gravitational field, distorting it wildly. The surface of the black hole, shown as a black ring, expands as it swallows some of the wave's energy. These strong ripples give way, and the black hole settles into a quiet state. In a supernova, the star's core collapses into a hyperdense ball, and its shell is subsequently ejected. Likely the most violent phenomenon in the universe, for a short time, a supernova outshines an entire galaxy. The expanding shell is disrupted by Rayleigh-Taylor instabilities, which in this case take the form of a lighter fluid supporting a heavier fluid against a pressure gradient. The interface between the two fluids is unstable, causing fluctuations to grow. The fluids mixing results in great turbulence. Users of the Hubble Space Telescope have observed that spiral galaxies, like our own Milky Way, sometimes evolve into much smaller elliptical galaxies. Supercomputer calculations show that this process can take place through galaxy harassment. 5 to 10% of galaxies, including the one we see here, exist in clusters. As they harass or bombard one another, many of the galaxies lose a large portion of their masses. The gas component undergoes great change, shrinking to a dense cloud at the center of the elliptical galaxy. This startling transformation occurs in fewer than 3 billion years. Cosmologists used simulations to test theories of the universe's formation. The best developed theory today is the cold dark matter model. Dark matter, so named because we can't see it, is believed to comprise up to 99% of the universe's mass. Cold dark matter moves relatively slowly, and many scientists hold that, together with gravity, it pulls visible matter into structures. In simulations, particles are used to represent dark matter. Here, 16.7 million particles clump together in a 325 million light-year cubic region of space. The clumps show where galaxies are likely to form.